recall what we did. First we had the notion of a partially ordered set. Then we introduced the notion of maximal and minimal elements. We introduced the notion of a chain. These were the fundamental ideas we had a partially ordered set, and we observed a partially ordered set may or may not have a maximal element. Have a maximal element. So our aim was to look for some condition which will guarantee the existence of a maximal element. Are you able to hear? Which light is off? This one? Perhaps the bulb is gone. You just switch on all the lights, you will know. Okay. So our aim was to look for some additional conditions that we may put on a poset that will ensure the existence of a maximal element. So some conditions on that will ensure existence of a maximal element. So this is what we want to know. Are there any such conditions that will guarantee the existence of a maximal element? In this context, we introduce the notion of upper bound and lower bound. So if S is any subset of a partially ordered set, U belonging to P is called an upper bound for S. For natural definition, if everybody is below it, for every S. Analogously, lower bound. If everybody is above, then it's called. It doesn't mean for every element in the partial ordered set, it works only for this sub collection. For all elements in the subset, S must be preceding U. Then U is called an upper bound. Common sense says if U is an upper bound, anything greater than will also be upper bound. That is, if U1 is such that U is related to U1, then U1 will also be an upper bound. No problem. Okay. But however, again, a subset may or may not have an upper bound. For example, a subset in a poset may or may not have an upper bound. Example, let us take the real line with the usual less than or equal to. All the real numbers with usual less than or equal to. Then, if we take the set S to be the open interval A infinity, then it has a lower bound. Lower bound is A, or anything less than A is a lower bound, but it does not have an upper bound. So, any R in R, such that R less than or equal to A is a lower bound, no upper bound. But now, if we take n, S to be only the positive integer, it has again a lower bound 1, but no upper bound. There is a unique, any real, any R in R, such that R is less than or equal to 1 is a lower bound, but no upper bound. Now, if you take S equal to Z, the set of all integers, positive and negative, there is neither a lower bound nor an upper bound. So, no lower bound. So, crazy things can happen in a partially ordered set. Some sets may have upper bound but no lower bound. Some sets may have lower bound but no upper bound. Some sets may not have either an upper bound or a lower bound, or some may have both. Now, what Zorn's lemma says is that in a partially ordered set, if certain types of subsets have upper bound, if you are guaranteed that certain types of subsets have an upper bound, then you are forced to have a maximal element on it. And the types of subsets that they talk about is a chain. So, Zorn's lemma says that if certain types of subsets of P have upper bound, then P has a maximum. And the types of set that they talk about are the chain. I'll write it here itself, certain types, namely chain. So, the Zorn's lemma statement therefore is, if in a poset every chain has an upper bound, then the poset will have a maximal element. So, let us take that. If the poset, every chain has an upper bound, then P has a maximum. So that's probably one of the most popular versions of the result to show that a partial ordered set has a maximum element. Okay, what I decided to do, suddenly I made my mind, I shall do two things which probably is normally not done in the first course in analysis, and certainly not in the first course in analysis for engineering students, probably graduate masters sometimes. But institute engineering students will always good in math. Probably I'll get one opportunity at least to talk about some of these things here. So what I am going to do is, in my course of action a little bit, talk about a few things which are connected with the Zorn's lemma, which are eventually different avatars of the Zorn's lemma, and also a different avatar of the Zorn's lemma being a different avatar of the so-called axiom of choice. I'd like to tread the path carefully because I haven't thought about how I will go about doing this. So what I'll do is start with a very simple idea to start with. Okay. So let me, I can apply this directly and get some of the result, but probably I'll deviate from the standard path. So to motivate what I am going to do next, let's look at something which you are all familiar with. So let V be a vector space over F. It has become a disease with me that any lecture I have to utter the word vector space at least once. So let V be a vector space over a field F, and recall the definition of a linearly independent set. If we have a finite set, we say it is linearly independent if the only linear combination that gives a zero vector is a trivial linear combination. But if it's an infinite set, we say that it's linearly independent if every finite subset is good. So therefore, let's now look at V, the collection of all linearly independent sets. Okay. So note therefore V is a collection of sets. V is a collection of sets from that vector space V. Now this collection has members who have a very peculiar property. Somebody can be a member if and only if every finite subset is also a member. Somebody is a member means is a linearly independent set. If it is already finite, no problem. Every finite subset is also linearly independent. If that member is infinite, by definition every finite subset is also linearly independent. So he should also be there. So V has the following property. Namely, a set V. Okay, let me write it probably in the context of what I am going to say. Let me make it more clear. V, note, V is a collection of sets. So usually a family of sets. Usually some more books write it as a family of sets, collection of sets. It has this, V has the property that the set V belongs to this collection of sets. The small b itself is a set. B, capital B, script B is a collection of sets. A particular set B will belong to that collection if and only if every finite subset of B is in B. That is also in that collection. Every finite subset is that, am I making sense? Okay. So you take B is the collection of all linearly independent sets. From that B you pick one fellow, he is a set. Take any finite subset of it, he is also in that collection. Any collection of sets which have this property, any collection of sets which has this property, that somebody will be in that collection if and only if every finite subset of that is also in that collection, is called a collection with finite character or family with finite character. So this is generalized into a definition. Let F be a family or collection of sets such that some A belongs to F. The set A is in that collection if and only if every finite subset of A is, okay, let me put it in a notation so that from now on I don't have to, if and only if K belongs to F for every K subset of A or K less than. For every finite set which is a subset of A, that finite set also must be in that collection. I was from 1 o'clock in the department there was no light. I come here, there is no silence here. Something is going on. So some either sound or light is after me today. Okay, so for example, take R, real line, and let F be the collection of all intervals of the form, just for the heck of it, A infinity, A infinity. So take all half infinite intervals, semi-infinite intervals, 1 infinity, 2 infinity, 0.5 to infinity. Take all possible semi-infinite intervals. This is a collection of sets. This is a collection of sets in R. This collection does not have that property, because if you take an interval of this type, any finite subset of it is not an interval of this type, so it will not be in that collection. So this is not, what did I say? I didn't say anything. Okay, then I should say here, then F is said to be of finite character. If this property holds, then it is said to be of finite character. So this fellow is not of finite character, whereas this fellow is of finite character. So then F is not finite character, of finite character. I'll just write, because a finite subset of an interval need not be is not an interval. Not even an interval, leave alone semi-infinite interval. So there are two types of families of sets. That is, one family has the property that whenever you include somebody in that collection, every finite subset should also be included in that collection. That is called family of finite character. I am going to give you two more examples which I will use. I hope I am giving the right examples because this is slight deviation that I have taken. So let me, I remember I once was teaching in IIT Madras, suddenly one day Professor Nikam was another department, said that tomorrow we will do a lecture on distribution theory. And I had a big program in previous day. I just went straight to the class. It was a lecture for the faculty. And I gave a lecture. At the end of it, Professor Nikam said, it was a wonderful lecture. Everybody understood everything. I said, because I did not prepare, I was going slow. We didn't know what I was going to say, so every word I said, I thought before I said, and again that gave enough time for people to understand. So today, probably I will go slow because I didn't think of this direction before coming to the class. So let me be a little bit careful. Some examples here and there I'll put back and forth. So, okay, let me make this V of the vector space example is of finite character. So there are families of sets which can be of finite character. There are families of sets which need not be of finite character. So I'll give you a couple more examples which will be useful for proving a few things. Let me give you example. One more example of finite. We have already seen a function from one set to another with the domain being a part of this set and the codomain being B. So let's make that. So let A and B be any two non-empty sets. Let FAB denote be the collection of all functions whose domain, I will take a subset, I will use symbols of A and codomain B. So let me use a notation right here. So let so FAB is the set of all functions from DF to B such that DF is a subset of, the domain is a subset of A. So it's like this, you take A and take B, take any patch in A and then define a function from here. Take all such possible functions. Okay. For every patch, you define all possible functions, select all patches, all functions, put them all together in a big box. That box is FAB. So the collection of all functions whose domain is a part of A and codomain is always, the values are always in the set. Okay. Now, this is not a family of sets. This is a family of function. So our character business talks about families of sets or a collection of sets. But what we are going to do is, we have already seen that we can connect a function with a set, namely the graph, which is a subset of A cross B. So let's now look at all the graphs. Instead of looking at the functions, let us look at the corresponding graphs. Both are synonymous. Instead of looking at the function, we can look at the graph. So let GAB be the collection of all the graphs of these functions, of the function. So probably I use the notation GAB is the collection of graphs of functions such that this function. Okay. So for every f, GF is a set, is a subset of A cross B. So for every f in FAB, GF is a subset of A cross B. Therefore, GAB is a collection of sets, collection of subsets of sets. The collection of, so what is GAB? Simply take a function, write graph, that graph. Take another function, draw the graph. But only thing is the function domain is part of A and the values are in the set. So now I have a collection of sets in A cross B, namely the collection of all the graphs of the functions coming from FA. This collection of sets that I have got, script GAB, I want to claim is a finite character. Claim now what should I show? What should I prove in order to show that GAB is a finite character? I must look at the definition. The definition says a collection is of finite character. The following property holds. Something will be in that collection if and only if every finite subset of that is also in that collection. So I must show that some subset of A cross B will be in this collection if and only if every finite subset of that is also in collection. So there are two things I have to prove. We have to prove that one, G is in GAB implies K is in GAB for every K in G with mod K. Every subset of G which is finite must also be in the collection. The moment G goes to the collection, here takes a lot of his relatives with him. If you allow the set G into this room GAB, lot of other fellows say we should also be admitted, namely all these finite vectors should be inside. Then the other thing is we have to show the other way around. Whenever every finite subset of G is in that collection, they say my elder fellow, the elder senior most fellow must also come. Is a group. So this is what we have to show. These are the two things we have to show in order that GAB is of finite character. Okay. So let's look at one. Let me very quickly explain. I will leave it as an exercise. Okay. I will explain one. The second one I will leave it as an exercise. Let me draw. The first one is G is in G. Now what is GAB? GAB is the graph of some function. So this G must be the graph of some function. So this implies there exists a function from df which is contained A to B such that the graph of f is this. Just to illustrate, I will draw a picture because these are abstract sets. Difficult to draw a picture of abstract sets. So let's say the horizontal line represents the domain set and the vertical set A and the vertical one. So let's say this is df and this is the graph. So when I say GF, I mean all these points. They are all in the A cross B. So that is what. So the moment G is in GAB, there must be a picture like this. E is the graph of some function whose domain set is a part of A. So this is A, say, this is the A direction, this is the B direction. All those points there are the points that make up the graph G, namely the set G. Now, K, we want to show this. take any finite subset of G. What is meant by finite subset of G? I take certain points. So let K equal to A1 B1 AN Bn be a finite subset of G. Now we want to show that whatever finite set you take, it must be in capital GA. So we want to show that A is in GA. In order to show that K is in GAB, I have to show that K is a graph. So in order to show that K is a graph, I must generate a function. Okay, I must generate a function whose graph is K and whose domain is a part of K. Is it obvious? Simply take the projections of these follows or A1, A2. So let dk be equal to A1, A2, An. Define K to be the function from dk to b as K of Aj. What is this function? This is just the restriction of F to the subset A1, A2, An. So K is this one. K is the restriction of F to the set. So therefore, and then K belongs to FAB and the graph of K is represented by K. Therefore, K belongs. Okay, so that's the first part. First part is that a set belongs to this family GAB if and only if every finite subset also belongs to that collection G. Conversely, the other part, if every finite subset of G belongs to GAB, then the whole set must also belong to. So let me just indicate that, probably just write down, a lot of time to this. Anyway, so the other part, so every finite subset of G is in, to prove that G itself. Again, to prove something is in GAB, you must always produce a function such that that fellow is the graph of that function. So, I want to show that G is the graph of a function. G is a subset of A cross B, right? How will it fail to be a graph of a function? How can a subset of A cross B fail to be a function of the graph of a function? Look at the picture. Suppose now I take some subset of this, let me put it this way, some subset of this. Will this be a graph? This will not be a graph because at some point it will take two values. So therefore the only way that G will fail to be a graph is that there is a pair AB, AB1, both belong to G, such that B is not equal to B1. So G is not a graph. So G is not a graph. Suppose G is not a graph. Suppose G is not a graph. This implies there exists AB, AB1, both belong to that subset. Because if for every A there is only one, you already have a function. So, this is the only way that G can fail to be the graph of a function. Now, this implies this is a finite subset of G. But every finite subset of G is in that, is given. Therefore, this must be a graph. But is this a graph? Cannot be the graph of a function because at A it takes two values. So, because it implies this must be graph of a function K for which Ka equal to B and Ka equal to B1. This is a contradiction. Because for any function, we cannot have two values in the same function. Therefore, our assumption that G is not a graph is false, and hence G is a graph. So, the conclusion therefore is that when you take the collection of all the graphs of functions whose domain is a subset of A and whose codomain is B, that G script GAB is a family of finite characters. That's an important family. Please go to a sub-win part. So is that clear? So these families of finite characters are real characters. Because if you allow one fellow, there are a lot of fellows you have to allow. That all is finite subsets must be allowed. And if you allow all these finite subsets, you must allow that fellow. Okay. So that's a very peculiar characteristics of these collections of sets. Whenever somebody belongs to that collection, every finite subset also belongs to that collection. So now we have a slightly non-trivial example of a family of finite characters. The first example of the family of finite character we had was the set of all linearly independent subsets in a vector space. That's what motivated the definition. The second example we have is the collection of graphs corresponding to functions whose domains are all subsets of a given set, codomain. Now the third example, which is again a very important example, which helps us prove something which we assumed much earlier. It is what we have seen is graph of function. Now I am going to look at the collection of graphs of some special types of function. Not just any old function, but special types of function. Now let me explain what it means. Let me just take a very simple example in the real life. Let's say I am going to draw the graph like this. That's the graph. Right? Now, if this function, if you take, let's say this height is 1. Or maybe some 10, but I don't think 0, 1, 0. Now, if you take any value between 0 and 10, there are 2 points at which this value is right. The same value is attained at 2 points. I don't want this to happen. What do I call such function? 1, 1. So, at every point, if it takes a value, nobody else, another fellow, different point, it will take a different value. So, I want to look at 1, 1 functions only. So, I won't allow such function, but I will allow a function like this, I will allow a function like this, and so on. So, what I am going to look at is f naught. Where was the example? F naught A is the set of all those functions which were as before with a specific property that F is. So it's a smaller collection than the one we looked at before. Previously we looked at all the functions. Now we are going to look at only one function whose domain is part of A and whose codomain is B. Now, corresponding to this we have graphs. Take those graphs and again use this GAB0 is the collection is GF, that's the F belongs here. The collection of all the graphs corresponding to one function, not all the functions. Now the graphs corresponding to one function. It turns out that this is also a family of finite characters. I will leave it to you as an exercise. Okay. Best thing to teach you is easy to see that E not is family of finite characters. So now we have three examples of this. We have seen the family of finite characters, the collection of all linearly independent sets in a vector space, the collection of all the functions from domain in A to codomain B. Now we write also and the collection of all one functions. What do we do? Wait for 2 minutes. Huh? Let's wait. The backup generator perhaps died. Oh, great. So your system is on. Right. So now we have these three examples. So there are lots of interesting families of finite characters. Now we'll see an important property of such families. Why we study these things is the following. So, important property of family of finite characters. So let F be let's consider any family now. Let F be family. What does this mean? Let's make it. First of all, F is a collection of sets. Okay? Remember that we always look at the property as collection of sets. F is a collection of sets, and this collection has the property that somebody qualifies to be in that collection if and only if every finite subset of that fellow also qualifies to be in that collection. So that's what I mean by saying that let F be a family of finite characters. And first of all, it's a family of sets. Okay. Whenever I say it's a family of sets. Now, whenever you have a collection of sets, you can always impose a standard partial order on that. What is the standard partial order? Subset or so F, since F is a collection of sets, F this subset or equal to relation will be a the subset or equal to relation is always a partial order on any collection of sets. Now, the moment you have a partial order, you can talk about chain. So now let's look at any chain. So let's see any chain in this partial order. What is meant by a chain in a partial ordered set? It consists of elements of that partial order. What are the elements? They are all sets. They are all sets. Every element of F is a set. So they are all sets and it's a chain. So any two are comparable. That means given any two sets in that chain, either A is contained in B or B is contained in E. So C, therefore C is a collection, a sub-collection of F, right? It's a subset of F. The chain is a subset of the poset such that any two sets in C are comparable with respect to the relation subset of C. Now the script C, every element of script C is a set. So there are many sets there. I put them all together in one box. Take the union of all the sets which are members of this C. So let K be union of all those sets C such that C belongs to this. Is that clear now? C here is a family F. F consists of several sets. Each member of this is a set. Now I am going to take a sub-collection of that, which are all sets which are comparable. Now I am going to take the union of all these. So every member of F is a set and C is a sub-collection of F. So every member of C is also a set and I am going to take the union of all these member sets of C. So this is a set. Finally K is a set. You don't know, probably let me use the K. Now, is this J in the collection? Is J in the answer is yes. The answer is I will keep them. So what is the property that we are trying to say? If you have a family of finite character, it becomes a partially ordered set. In that partially ordered set, you take any chain, then the union of all those fellows in the chain is also in. Is that clear? Messy statement. I have this collection of sets. Each one is a box. Now among those boxes, I choose certain smaller collection of boxes. This smaller collection of boxes are comparable. That if you take two boxes, either all the contents of this are in this or all the contents of this are Now what I do is, in the smaller collection of boxes, all of them I pour in a bigger box. Now that bigger box is a set. Will that be also a box somewhere sitting here? And the answer is yes. That will also be a box sitting in that collection of boxes. There is a collection of boxes. In the collection of boxes, I choose a smaller collection of boxes. The smaller collection of boxes pairs are comparable. Now I take every content of the smaller collection of boxes and put it in a big box, and then bingo, I find that big box is sitting somewhere there. Maybe, definitely it may be sitting outside. It could be sitting outside the smaller collection, but it is in that big collection. Certainly it is there. That's what I'm asking. Is J sitting somewhere here? If you put all these things together and make a big lump, that lump will be one of the elements. So the union of all those elements J will be here, and this element C, the union of all those elements will also be somebody there. It's clear. So in a family of finite character, is always a family of finite character is always made into a poset with respect to the partial order subset are equal to. In that poset, you take any chain and put all the members of the chain together and take their union. The resulting set will be back in that collection which we started. That's what the fundamental property of families of finite character. Yes. Yes, right. Why? Because this is something, that is a hand-waving proof. How do you say that? So therefore you are saying the union of every element of the chain must be in the chain. You think carefully. Think carefully. It's just be true. The union of every element in a chain must also be in the chain. And that was all the big problem. Okay? That is why all this Ramayana is there. That's not necessarily. Think carefully. Construct examples. Take n. Less than or equal to. Right? Take all finite initial. That is a chain. 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, all finite initial. That's a chain. What is a chain? It is a finite, is that a finite initial segment? Is that in the chain? Now put this example, put these things together and do some sleep in the night, okay? Then we will understand. So the union of elements in a chain need not be in the chain. If you have a partially ordered set set consisting of set and with the subset are equal to relation, then if we take a chain, the union of the elements in that chain need not be in the chain. They will be sitting outside. Now when they are sitting outside, what I am saying is they may sit outside, but when they sit outside, they don't sit too far outside. They are sitting within that bigger box. Bigger circle. Is that clear? Where was I? The answer is yes. This is a thing which we can prove. I will again hold it for a moment. I'll just look at a consequence of it. The consequence of this property is what is known as Tukey's lemma. the Tukey's lemma, we will state it, we will prove it using one-line proof using Zorn's lemma, but the other way around also possible. You can prove Zorn's lemma using this, so it doesn't mean that which one is one. If this is fundamental or that is fundamental, this is not here. Both are equivalent. You have to have one, you have to have all of them. Okay, so now let me make a statement. Okay, let me state the Tukey's lemma after we use it and get a conclusion. So what are the ingredients that we have? We have the notion of a family of finite character. The problem is that I know that you lose sleep tonight. If you lose sleep about a particular problem, then you are in the right direction. If you don't lose sleep about a particular problem, then you are in the wrong direction. You have no direction. Anyway, what was it? Okay, so the ingredients that we have is a family of finite character, and a specific property of the family of finite character, namely that a family of finite character becomes a partially ordered set under the subset are equal to partial order, and in that poset, if you take any chain, the union of the elements in that chain are again back in that. That is what the fundamental is. Now, let F be a family of finite character. Therefore, F is a poset. Let C be any chain. Then by that result, then J equal to union of C, that C belongs to C, is also in F. Therefore, C is a subset of J for every C in C, and J belongs to F. What is your conclusion? What is your conclusion? All you have said is take any chain C, then the union of those fellows is in F, and that union stands to the right of everybody in that chain. What do you call that property? Upper bound. J is an upper bound for C. Therefore, J is an upper bound for C. So what does that say? In the partially ordered set F, every chain has an upper bound. And Zorn's lemma said whenever that happens, it should have a maximal element. Therefore, the partially ordered set F will have a maximum. What it says is, if you have a family of finite character, in the partially ordered set F subset are equal to, there will always be a maximal. That is what is known as Tukey's lemma. So, that's it. Therefore, I will continue. J is an upper bound. Thus, every chain in a view has upper bound. Therefore, by Zorn's lemma, F is maximum. This is called Tukey. F is the family of finite character, then F has Lemma. Okay. I will finish one more thing. There are many more things to be said. Then at the end of it, I will. So this is the so we see Tukey's lemma as a consequence of Zorn's lemma. Finite character property is the one that gives upper bound for chain, and Zorn's lemma says whenever you are upper bound, then you are guaranteed a maximal. That upper bound of chains has to be guaranteed. To guarantee a maximal element, you have to guarantee an upper bound. That upper bound is guaranteed by this finite character. So it is a finite character property that guarantees the upper bound. Okay. I will discuss next class two applications of this. One is the existence of the so-called Hamel basis for a vector space. But I will discuss also one more example, one more application of it, which probably in the first or second class I just glossed over and stated. Namely, I said that if you give me two sets A and B, let's say this all next class I will do, so just I will not write the detail. So application of Tukey's lemma of EL. One, existence of Hamel basis for a vector space. The second example that I will discuss is the following. Suppose you have two sets A and B. We said that the cardinality of A must be less than or equal to the cardinality of B, or the cardinality B must be less than or equal to the cardinality of A. In other words, we said that the law of trichotomy holds for cardinality. That is, if you give me two sets, either they are equivalent or one is putable in the other, but the other is not. This mod A equal to mod B, or mod A less than mod B, or mod B less than mod B. Or in one word, either mod A less than or equal to mod B, or mod B less than or equal to mod B. That's called the law of trichotomy. What can it not happen that I have two sets such that neither I can put this into this, nor I can put it. That is, can I have two sets A and B such that mod A is not less than mod B, mod B is not less than mod A, and mod A is not equal to mod A. And we said this will not happen. That we will do using then for any two sets, what any two sets A, B, the law of trichotomy mod A less than or equal to mod B, or mod B less than or equal to A. It's not a trivial, therefore this fact is not trivial. We have to go through several iterations, get to do this lemma. And so here, for this, I use that B, the script B, a collection of all linearly independent sets, and I observe that that is a set of a collection of finite order, and therefore I can apply Tukey's lemma and get a maximum linear. For the second one, I will apply the other one, F naught AB and G naught AB, the graphs of all 1-1 functions. I will use that family of finite characters to establish this part. And there is one more of the property of finite characters, and Tukey's lemma also gives rise to something called Hausdorff's maximality. It's about the existence of a maximal chain. It's the existence of a maximal chain. That is what a chain in a poset which is not the proper set of any other chain. Maximal is a chain. It is maximal in the sense you cannot put it in the another chain. You cannot embed it in any other bigger chain. So that's called the Hausdorff maximal. So you get lots of things. One, Zorn's lemma. Other is Tukey's lemma. The third we'll get is the Hausdorff maximality. Then we'll see what is known as, now that I have decided, because this was not planned, now that I have done this, let's go full steam. Maybe once in your life, what is known as very profound, very interesting things in set theory. There is something called well ordering theory. There is something called well ordering. And then corresponding fact that every set is well ordered. The order that you have in mind may not be well ordered, but there is always a well ordering. So then we have four: Tukey's lemma, Zorn's lemma, Hausdorff maximality, and then the well ordering. Finally, we get the choice. And we show the equal factor. This is true, this is true, this is true, this is true. So therefore, we don't know which is. So make an axiom that one of them is true. Therefore, all of them. So it's a big bonus. So that's the axiom, which therefore we make it as an axiom. That is how it came. The axiom of choice came in a very peculiar manner because of investigation set theory. And then they got Zorn's lemma looked very natural, possible. But then they realized that they were experimental. Tukey's lemma looked natural, but that was again equivalent to axiom of choice. So they thought they proved axiom of choice using well ordering theorem. But then they said to get well ordering theorem I need something. To need that I need something. To need that I something. And to need that I need that. So it went round and round and round. So we have therefore several equivalent versions of the axiom of choice. For some reason, the way it is known that choice function is called axiom, Zorn's result is called lemma, Tukey's result is called lemma, Hausdorff's result is called principle, and the well ordering result is called theorem. It's a very strange thing, because that shows at that time they believed that it was a theorem until the equivalence was established. So these are all some very strange things that happened as you go through abstract set theory to get these things settled. So finally the axiom is actually added. So the way that one works with in analysis is the Zermelo, Frankel, axiom of choice, continuum, hypothesis, set theory. All these we take for granted. The original axiom was the Frankel, the axiom of choice added to it, and then the continuum hypothesis added to it. With all this, we will work through analysis. The analysis that we do is subordinate to these axioms. We remove any one of these axioms, we do some other. Alright, so the next class, what I will do is I will quickly go through these two examples and very quickly illustrate the other equivalent version, and finally probably make the axiom of choice surprise all of us that this is what you are saying, and that probably will be concluded once I finish axiom of choice, that theoretically.